All right, hello everyone. Welcome to Unit 3, Lessons 2 and 3 of our complex number and exponent unit. Um, we're going to do two lessons together here because the two are very well linked and they're pretty short, so we'll kind of put them together into one video. If you're here for lesson 3, just skip forward to the next chapter. All right, so this first lesson is a quick one, just as a quick little uh, reminder of what a square root and a cube root are, and how they interact in creating values and figures and how to evaluate them. All right, so with that in mind, let's start off with a little problem, shall we? I have a square, and inside that square, I have a smaller square, but it's crooked, right? And can you find the area of the square? Hmm, Well, to find the area of the square, well, how do we find area of a square? Area is equal to length times width, right? Length times width. Now, it's also equal to length squared because, these are going to be the same length. Now, how do we know that they're the same length? It's because of the fact that these four triangles are congruent triangles. How would we know that they're congruent triangles? Well, we have a square. We're being told that these are all right angles. And since we have twos and threes, basically we can show that even without the hypotenuse, we can show that the four triangles are congruent by SAS. If you remember your old geometry stuff, we can show that all four triangles are congruent, what we call the side angle side theorem. That means that these four hypotenuse, then hypotenuses, something like that. Well, they're all equal. And so we know at least that we have a rhombus. We can then show, how would we prove that these are right angles? Well, you can prove that these are right angles by simply realizing that this is a right triangle, right? So this angle have to add up to 90. But that this angle is equivalent to this angle over here. So I'm going to mark those like that. So these two angles therefore add up to 90. Therefore, this must be 90 degrees. This is 90 degrees. So a little bit of a side note here. We can prove that this is in fact a square. But anyway, that's kind of besides the point here. Just fun little fact here. You can prove that fact. But now, can you find its area? Well, what else do we know about triangles? We might know our old friend, the Pythagorean theorem. And so applying it to one of these triangles, we have 2 squared plus 3 squared equals c squared. 4 plus 9, that's 13. And so c is the square root of 13. Now, here, again, the square root, what is a square root? A square root is a number such that when you multiply it by itself, it gives you some target value. So the square root of 13, when squared, gives us plain 13. Now, the square root of 13 is a decimal. It's somewhere between 3 and 4. We know that because square root of 9 is 3, and the square root of 16 equals 4. So root 13 is going to be somewhere in between 3 and 4. But that point is kind of moot here because we want to find the area. And if we know that this is root 13, and we know that this is root 13, what's the area? Well, square root of 13 times the square root of 13 is going to be plain 13. So the area of the square is 13. Now, every so often, I'll get a person that says, hey, well, can't I just subtract off the areas of the four triangles from the bigger square? Well, sure you could. Um, the area of each of these triangles, so it's going to be 2 times 3 divided by 2. So the area of each one of these happens to be 3. 3, 3, 3, and 3. And so the whole thing is going to be 25. 25 minus 12 is 13. So you can find area either way. But this way, using the Pythagorean theorem, illustrates a property with roots that's very important. And this is a very general property. Notice that when I multiply square root of 13 times square root of 13, I do get a plain 13. And I can generalize that to say that the root of n times the root of n is equal to just plain n. And that's true for any number n. Okay, next idea. So using that fact, let's see if you can now figure out the area and side lengths of some of these squares. Now, some of them are pretty easy, right? I mean, we're going to assume that we're dealing with units. So each one of these is considered one unit, right? So if that's considered one unit, well then, A is easy, isn't it? Its length is 1, and its area is 1 square unit. C is another easy one because it's sitting right on grid lines. It has a side length of 2 and an area 1, 2, 3, 4. Now, what about B? Let's look at B. So in this one, it's turned sideways. So we would want to know how big one of these sides is. Now, you may be able to look at this and say, well, hey, you've got half a triangle. It looks like you've got 4 triangle halves, right? And if I put 4 triangle halves together, I get an area of 2. But now we can actually prove it. So if I look at one triangle piece from this, right? 1 and 1. I can also apply the Pythagorean theorem, can I not? And 1 squared plus 1 squared is 2 square root of 2. And this is the 1, 1 root 2 triangle. Sometimes this is called the 45, 45, 90 triangle. This is a special right triangle. Again, for those of you that took geometry already, then you certainly might recognize that one. And that is huge for SATs. Knowing that triangle, definitely important on the SATs, okay? All right. So that length here is going to be square root of 2. And sure enough, what's the square root of 2 times the square root of 2? It's 2. So it works. Let's look at D. Same idea, right? But this time, look at the triangle that I can create from here. It's got 2 legs, a 1 and a 2. 2 squared plus 1 squared is 5. So that's going to be root 5. Interesting. So let's look at this side length, root 5. So what's its area? 5. Now, if you want to look at this visually again, you can also look at this in another interesting fashion, right? So looking at the area of this, here's 1. Now, this triangle here is half of 2 squares. So that triangle has an area of 1. So it's 1, 2, 3, 4, 5. Area of 5. What about this one? So again, you might realize here that you have squares here. And so 1, 2, 3, 4, half, half. So this is a whole triangle right here. So 4, 5, 6, 7, 8. It's got an area of 8. Now, what about its side length? Again, we can use Pythagorean theorem here, or we might know at this point that it's just going to be the square root of 8. And again, you can use the Pythagorean theorem to prove it, right? Because you're going to have 2 and 2. And so you get 2 squared plus 2 squared. Well, 2 squared plus 2 squared is 8. So this will be root 8. Interesting. Okay. So again, there's the connection there. So 8 versus root 8, 5 versus root 5, things like that. So remember, Any number in a radical, when you multiply it by itself, it does equal the original number again. Doesn't matter what it is. Okay, now let's go on to 3 dimensions. Talk about cubes. A cube has an edge length of 3 units. Think of Rubik's Cube, right? If you were to take a Rubik's Cube apart, how many pieces would it be? Well, let's see. Volume of a cube, we did this not too long ago. Volume is length times width times height, 3 to the third, 27 units cubed. All right, what about 4? So 4, well, we'll have 4 times 4 times 4, 4 to the third, that's 64. Now, what if I had a cube whose volume was 8? What number to the third power is equal to 8? 2. 2 times 2 times 2 gives you 8. What about 7? Oh. Oh. Uh, it's got to be less than 2. But let's see. We know that 1 to the third is 1. 2 to the third is 8. So this will have to be somewhere in between 1 and 2. Maybe, I don't know, a little bit closer to 8. 1.8, 1.9. But it's a decimal. Now, in this case, though, we might say, oh, well, kind of like before, we have the area, and we were able to write it as the side length as a square root when it didn't work out even. But we're not dealing in squares, we're dealing in cubes. So at first, it might make sense, to write it as a radical. However, that's a square root. To signify that it's a cube root rather than a square root, we're going to use a little 3. And the little 3 is going to sit in the crook of the radical to illustrate that we want to know what multiplied by itself 3 times gets you 7 rather than just twice. So the difference here, so square root of 7 is, x times x equals 7. But the cube root of 7, x times x times x equals 7. And so in those cases, it would be a different number, right? And as you can tell, it would have to be a smaller number. So that's a signify for what we call a cube root. And it's the number such that when raised to that particular power, or third power, you get your regular under the radical number. This can be extended to 4th roots, 5th roots, 6th roots, 7th roots, whatever root that you would like. So you can extend this to, a 4th root, 5th root. So if I wanted to write, say, the 7th root of 10, then that's, x times x times x times x times x times x times x equals 10. And that's got to be a pretty small number. So that 7 multiplies will only get you to 10. So that's the definition of what we call the nth root, of which cube root is just kind of a small little piece of it. Okay, so for our purposes here, we're going to stick to cube roots. Square roots and cube roots are the ones that are more likely to encounter in life. You might see a few other ones out there, especially, 4th roots maybe. But square roots and cubes are always good to have, like some of them in your mind, simply because, they involve area and volume. Okay, so no, now I don't expect you to know the cube roots of numbers, right? Like even I don't know like what the cube root of 85 is, but I can estimate it based on where it is in relation to integers. So for example, the cube root of 1200 is between 10 and 11 because 10 to the third is 1000 and 11 to the third is 1331. So the cube root of 1200 is probably going to be closer to 11 than it is to 10. So that gives you a little bit of information as to like what you could see. So I would definitely say it's between 10.5 and 11. I'm pretty confident at that. And that's probably a good enough estimation for that until I use a calculator. So let's try some other ones, right? For example, the cube root of 5. What's the cube root of 5? Well, don't know, but we know that 1 to the third is 1, and we know that 2 to the third is 8. So we know that the cube root of 1 is 1, the cube root of 8 is 2, the cube root of 27 is going to be 3. So cube root of 5 is going to be between 1 and 2. Cube root of 10 is going to be in between 2 and 3. Now, probably definitely closer to 2, right? So just a little bit higher than 2. Uh, let's keep going. 4 to the third is equal to 64. So cube root of 50 must be in between 3 and 4. Now for 4 and 5, so for 4 and 5, we have, um, is it going to be cube root of 100? Well, let's see the next one, 5 to the third is 125. So yes, certainly this will be in between 4 and 5. What about the cube root of 500? Well, the next few after this are 216, 343. It's going to be higher than that. And 8 to the third, 512. So the cube root of 500 is almost 8. It's like 7.9 something, I believe. So it's going to be here. Okay, so just estimating roughly what some of these values are based on their placement is, a very powerful skill to have, right? Okay, so let's find some solutions to some of these equations, right? So remember that when I solve equations, right, this is where we sometimes have to worry about pluses and minuses. Okay? So for example, if x squared equals 25, well, what could x be? Well, remember our work in quadratics, x would equal plus or minus the root of 25, x equals plus or minus 5. And the same thing holds true, for any time we have to undo a square with a square root. If we try to undo this, we get z equals plus or minus root 7. And remember what I said when I just asked you, what's the square root of 7? Or what's the square root of 25? No, that's just simply 5. But the plus or minus sign comes into play when we have to solve an equation by taking a square root. Okay, so for the next one, let's look at third power. So what to the third power gives you 8? Well, it's 2, right? So is it plus or minus 2? No. And that's because what if this were negative 2? Negative 2 to the third power, well, negative times negative times negative is negative. That means that there is no plus or minus here. The third power has one interesting advantage to it in the fact that you never have to worry about pluses and minuses. you can take the cube root of a negative number. So the cube root of negative 8 is equal to negative 2. So cube roots will preserve signs, as because cube does too. And then finally, the last one here, so w will just equal the cube root of 19 again. So we're just undoing the operation of 3. And again, no plus or minus sign, which is nice, right? So it turns out this is an interesting property that happens. You expand a little bit upon this when it comes to this. So even powers and roots. Um, you might need a plus or minus sign. If you solve an equation by taking even power or an even root, so a second root, fourth root, sixth root, eighth root, plus or minus is possible, and that's because of the fact that, negative sign cancels itself out in pairs. And if you have an odd power root, then you don't have to worry about the plus or minus sign. You just keep the sign that you have. All right. I believe that ends our lesson number 2. All right. So I hope that that was fun. And this is where we'll take a quick 2-second break and start lesson 3. I'm enjoying a good cup of tea here. Unlike the last video I did where, unfortunately, my cup of tea was ambushed by a ladybug, this time, I do not seem to have that problem. My recording room seems to be ladybug free at the moment. Of course, now I probably jinxed it. All right. So for this lesson, we're now on lesson 3. Lesson 3, uh, we're going to take the idea of a square root and a cube root one step farther, because it turns out that they have a major connection to exponents themselves through the use of the properties. So what we're going to do is we're going to set the stage for something that mathematicians tend to deal with, right? So over the last couple lessons, we looked at exponents. And what is an exponent? An exponent is physically the number of times that you multiply some number by itself, right? You can also think it's like the number of times that factor appears. So 9 squared is 9 times 9. 9 to the first is 9. 9 to the fifth would have 5 factors of 9. But then we defined, so, and I'll write those down here. So we have 9 squared, that's 81. We have 9 to the first, that's 9. 9 to the 0, that's 1. And then because we said, well, what happens if we had no factors of 9? Well, without factors, then all we're left with is the identity of 1, because 1 is always present when you divide away all other factors. And so we were able to extend the definition to 0, and then from that, we then extended the definition even to negatives by saying that we're dividing by 9 each time when we make the exponents go down. And so we get to 9 to the negative versus 1 over 9. And then we created that exponent property, right? Anything with a negative exponent is reciprocal of the same term with the positive exponent. So all that's all well and good. So mathematicians always like to extend the thinking beyond the physical realm to say, well, does the math work? How far can I extend it into something that may not be physical? So we were able to define 0 exponents, negative exponents, even though like you can't multiply something a negative amount of times. So the next logical step is to deal with fractions. So what if I had 9 to the 1/2 power. So halfway between 0 and 1. Could that get a value? Well, possibly, right? So let's see what we can do with that. To handle this, we're going to draw a graph. And so we're going to sketch a graph of these values, right? We're going to graph the function y equals 9 to the x power. So I'm going to have 0, 1, 2, 3. And I'm going to set them that distance apart for a reason. So that I can see, like, I can get into the fractions of it. So here would be a half, right? Okay, so let's graph some of these. Let's graph the ones we know. 9 squared being 81, though. This is going to have to extend pretty well up. So we're going to go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 60, 40, 20. Okay, so across a 1. Now, 9 to the first is 9, right? But the 9 squared is going to be 81. So it's going to be like right here. The next one's going to be way off the chart. So we don't even have to worry about it. But what we can do is we can sketch a graph of what this might look like. Oops. Okay, so yeah, kind of. I know it's not the greatest, but we can Desmos this in a bit. Okay, so it's kind of hard to do this with the stylus, I admit. But what we try to do is estimate what we get for 9 to the 1/2 power. Well, if you look at where that line goes, right? It looks like it's going to be somewhere around 5, maybe even a little bit less than 5. I wonder what could happen. A little bit less than 5, maybe? Let's look at Desmos. We'll see what that says. Okay, so Desmos, when I do this, let's type in y equals 9 to the x power. Okay, so there's my graph. Okay, and it's a very steep graph, right? And that's because, just going over to 2 makes the graph shoot up to 81. So anyway, let's scoot in here. So here is 9, right? And so here, let's bring this down. Here's 0.5, right? So 0.5 power, 3. It's 3? Well, it is less than, certainly less than 5, so we're kind of right there. So coming back to this, here, do I have, oops, I think I have to, oops, that's why I was not writing in the right spot. 3. Well, why is that? So look at this chart here. Isn't it true that if I go from 9 to so 9 to the first and 9 to the second, and multiply by 9, oops, not 3, multiply by 9. To go from 0 to 1, I multiply by 9. To go from this way, I multiply by 9. But look at this pattern here. 1 times 3 is 3, and 3 times 3 is 9. So is multiplying by 3 the same thing as multiplying by 9? I think it might be, because 3 times 3 is in fact 9. Interesting. So let's see if we can prove this fact. Okay, so one way we can do this is by using negative exponents, or sorry, fraction exponents and the properties of exponents, right? So what happens if we have the term 9 to the 1 half times 9 to the 1 half? So one way that mathematicians try to figure out whether a number is legitimate and what a number could be as another value is they attempt to assume it's a legitimate value and apply properties to it. So if this is an exponent, right? And we already know that the exponent properties work. So we can take 9 to the half and multiply it by itself, even though we don't know its value. So we can still do math on things that we don't know their true value. We do that all the time with x, don't we? So 9 to the 1 half times 9 to the 1 half, well, what would that be? Well, remember, same base, add the exponents, and 1 half plus 1 half is 1. So that must be 9. So two things multiplied together, two of the same thing multiplied together gets you 9. Well, the only number I know that does that is 3. So, yet, 3 times 3 gives you 9. We already know that. So, 9 to the 1 half must be equal to 3. Interesting. Okay. Well, what if we try something different? Now, 9, one thing about 9 is a perfect square, right? But what about 3 itself? What about 3 to the 1 half? All right, let's try that. So this time, though, rather than going on here, let's just go right to decimals for this one. And let's just change this to 3 to the x. Okay, now we know that this one, 3 to the first is going to be 3. And we know that if we scroll up here, that yes, 3 squared is 9. We know all that. But what about the half? We get, oh, it's decimal this time, 1.732. Okay, 1.732. So once again, let's try to apply the properties to it, shall we? So we're going to get about for this one about 1.732. And again, you can draw the graph here, but for the sake of brevity, oops, 1.732. Now let's try using the same methodology that we used before. So 3 to the 1 half squared. Okay, we don't know what the square root, we don't know what 3 to the 1 half is. We don't. Let's say we don't know its true value, but we square it, right? So 3 to the 1 half power is squared. Well, what happens? Power of a product property. So therefore, we get 1 half times 2. That's 1. This is equal to 3. Hey, so now what we're saying here is that some number squared is equal to 3. Well, what's multiplied by itself gets you 3? Root 3 times root 3 must be equal to 3. Fascinating. And that's going to give you one very important property here. Okay. So we have two important properties that we looked at. Property number 1, square root of n times the square root of n is equal to n. Okay. We did that in lesson 2. This is from lesson 2. Now we know this one. And it turns out that power of 1 half, so n to the 1 half power is equal to the square root of n. So we have determined that 3 to the 1 half, the only way that that works is if it's equal to the square root of whatever this base is. It worked for 9 because 9 to the 1/2 we found was 3. And the square root of 9 is 3. So now my next question is going to be, could we do the same thing for cube roots? So what if I went back and I looked at changing this fraction up a bit, and maybe I'll now do try n to the 1/3 to the 3 power. What would that be? Well, that would be n, right? So something to the 3rd power is going to be n. Well, that's the definition of a cube root. So rule number 3. So we're going to extend this rule, and we're going to say that n to the 1/3 power is equal to the cube root of n. So some very important properties here that are super good to know. So the cube root and the square root can be represented by powers of that particular number. Now, why might this be important? You might wonder, well, what do we need to have like a square root and an exponent be the same? Well, what this does is it gives an equivalence between two forms. And there are going to be some cases where a problem might be beneficial written as an exponent, and there might be some cases where you may rather have a square root. Um, but one thing that it does, if you have like numbers written all with radicals, you can figure out how some of those compare to each other, maybe by converting them into exponents and maybe being able to compare them in a different way that way. So, there's lots of cases in math where we have, um, the same numerical value can be written in several different ways, depending on, you know, what's important. Okay, so let's try it out, right? So what's 25 to the 1/2 power? Well, that's equal to the square root of 25, but you don't even have to think square root of 25, just say 5. So when you see a power of 1/2, immediately think square root, right? Uh, Square root of 15 is just square root of 15. Now, again, with these ones, because you're dealing with square roots, you could make the case as possibly a -5. Um, the problem, though, with that is it's not very continuous in terms of the function itself. Um, for these, again, because we're not solving the equation, we're going to really stick to the positives here. 8 to the 1/3, though, we won't have a problem with that. What's the cube root of 8? And then the cube root of 2, well, it's just the cube root of 2. We don't know that's a decimal. Okay, so that's really where these 1/2s and 1/3s come from and how they relate to radicals. All right. Match each exponential expression to an equivalent one. I think we could totally do that now. Um, so think about this way. When the powers go down, right, the highest power should have the highest value, right? So 7 to the 3rd, well, that's 343. 7 squared, we know 7 squared is 49. 7 to the 1st, well, that's just going to be 7. 7 to the 0, well, anything to the 0 power is 1, right? Okay. 7 to the -1st, 7th. 7 to the -2. Well, 7 squared is 49. So 7 to the -2, 1 over 49. 7 to the -3rd. Now again, with exponents, right? So an exponent of 1/2 means square root. They are equivalent. But what about a negative 1/2? Well, remember that a to the negative m is equal to 1 over a to the m. So a to the negative 1/2 is 1 over a to the 1/2. So it's going to be 1 over the square root of that number. One-third exponent, that's cube root, and a negative exponent fraction. There we go. Easy enough to match them up, I think. There we go. Okay. And so there is an introduction for you in terms of half powers and one-third powers. Um, so I think from the next step is going to be, can we define this for general exponents? And maybe now we've dealt with 1/2 and 1/3, could we define it with 1/4, 1/5, or even such fractions as like, could we even come up with a to the 2/7 power? What would that look like? Um, and that's going to be coming up soon. Okay. But these two rules here, I know it's a little bit kind of tough to see here, so I'll go back and again revisit uh, this slide here. These three rules. This is the big idea. Okay? All right. And we're going to use those rules and extend them even further during the next few lessons. So have yourselves a great time, folks, and I will see you soon. Have fun.